Okay, so the next talk will be by myself. This is a modeling study, as mentioned this morning by Huang Xiong. We are developing a regional and for the aerosol cloud scheme for regional and global models. And today I'll only show you the regional model results. This is the structure of our project. We'll be working on first the regional model, cloud microphysics, aerosol microphysics, and their coupling. And in the future, hopefully, we can put all those schemes into the global model, and so that the global model, different clouds in global model have consistent microphysics. And today I'll focus on this part. This is the microphysics scheme, which is very similar to typical bulk water scheme in regional models. It consists of the different hydrometeors, including cloud drops, rain, liquid phase, and 3 ice phase. But in this scheme, we also spend a lot of time to incorporate the aerosol cloud interaction, including condensation nuclei activating into cloud drops. And also we have a scheme for calculating the giant condensation nuclei, which can directly activate into raindrops. Another effort is spent on the ice nuclei, which is the biggest unknown in the regional cloud microphysics. And in the past, usually the ice nuclei are specified or use empirical equations, but in this study, we try to actually simulate different kind of ice nuclei. So I will show you some snapshots of the results from these our regional models. And since Professor Wang already mentioned Chen gave some sensitivity study on the other aerosol effects. So here I only show you one example of our new results showing the aerosol effect on typhoon. This is a very special typhoon, Nari. It's circling around northern Taiwan for about 1 week, then goes south. Okay, usually go north, but this one goes south and then from Taiwan. Since it stayed here for quite a long time, I was suspecting that the aerosols in Taiwan, in Shanghai, and the mainland China probably will get into these clouds. So we did some simulation, and this is the first simulation. We use specified aerosols. One is the urban type of aerosol, and the other is maritime to initialize the model. Okay, that's specified. And the black curve is the observed track. And you can see different aerosols and even different cloud scheme give you different track. This is the very popular scheme in the current WOLF and the MN5, the WN6, which is, I think, is pretty good scheme. But we'll ignore that. We just compare the urban and maritime. The maritime goes this way to the eastern Taiwan, but the urban type goes to the western Taiwan, much closer to the observations. And due to the change of the different tracks, you can see the precipitation also changes. The maritime case, it goes to the east, so the precipitation focuses on the eastern part, northeastern part. But urban case, it has a lot of precipitation in the north, which is closer to the observations. So this case, it shows aerosol can affect the track of typhoon for this special typhoon. But we did some other simulations that the aerosol effect on fast-moving typhoon is weak. Okay. Another thing we want to compare is the microphysics. So we compare the rainfall during landfall in Taipei, since during that time the NCU has some disdrometer measurements. We can compare the drop size. So this is the observed radar reflectivity, and this is the simulated radar reflectivity from the urban aerosol case. We try to compare this one. And here are the mean volume radius of the simulated rain. And this one should be the urban type. And this one is the maritime type. I was expecting to see smaller raindrops in the urban aerosol. However, I don't see it here. Okay, both the urban type and the maritime type are falls around 1 millimeter size. This one is simulated by the WDM6, which I was considering as one of the best current microphysical scheme in WRF. However, it produced very small raindrops, only 0.1 to 0.2 millimeter. Okay, and the dashed line shows observed range, as shown here. The black dots here, the mean volume radius, it falls between 1 to 2.2. So our scheme produced very good results. It fits the observation very well, but not other schemes. And we also tested other options of the microphysics, which should give you much less, even less particle size. So this shows you the importance of including aerosol and cloud-coupled microphysical scheme. And now we are in the process of coupling the aerosol and cloud scheme. So we have cloud scheme and the aerosol scheme SNAP. And a few minutes ago, I just found out these two schemes has been officially combined into SNACs. Okay. So we try to simulate the same typhoon using real aerosols. Okay. And here are some new results. These are the natural plus anthropogenic aerosols. And these are only natural aerosols. You can see the structure of the typhoon is very different. Okay. The anthropogenic effect on typhoon make the typhoon larger, much broader. And I won't get into the details of the dynamics because there are very interesting microphysical effect on the dynamics. However, we don't see much change in total precipitation. Okay, that's another very interesting issue. I don't have time, so I will skip that. We can discuss about that after the meeting if you would like. Another effort we spend is the ice crystal shape. As Professor Paul Wong mentioned, that aerosol has shape, but cloud particle also has very complicated shapes. And none of the current model consider the shape of the ice crystal, which is, I think, is the major deficiency of the models. So here is the first attempt to include the ice crystal shape. Not only include it, but also it can evolve naturally with so-called adaptive growth method. So this is the wintertime snowstorm case over the Great Lakes. Okay, this is the cross-section A to B, and we show you the profile of the cloud ice and snow. See, there are two layered clouds. Okay, and here we show we can simulate the ice crystal aspect ratio. The blue is the place, and the green are the current type of ice crystals. So we are in the process of comparing with some of the aircraft data, and I think our results are pretty good. And this diagram shows the vertical profiles of the hydrometeors, the cloud ice, snow grapple, cloud drop, and rain. And here are several different schemes, the Morrison, WDN6, and our scheme. Our scheme actually, for the shape, we used it on Morrison scheme. You can see different schemes give you very different results, but also if you include shape, it also gives you very different results. So the shape effect on the cloud microphysics is very significant. And we calculate that the radiation budget change also are very significant, but I won't show you the details. And the next part is the aerosol schemes. We call it SNAP. This aerosol scheme, we applied a non-conventional approach. We actually use a very fine beam model, not sectional, but very fine beam, hundreds of beams, okay, to do offline calculation first, then convert results into parameterization formulas, okay, using statistical analysis. And we also consider the mixture of different aerosols, which Chen already mentioned is very important. And there will be one poster session discussed on one of the mixture effects. here are the results of our SNAP method. The horizontal axis is the exact solution for, I think here we use the Brownian coagulation process. Exact solution, and this is calculated results for different schemes. SNAP A is the most simple scheme in our method, and SNAP C is the complete method. Okay, and the BS95 is the currently used scheme in the CMAC and in WolfCam. And the GHQ is the Gaussian quadrature scheme, which is a numerical integration, should be very accurate. And it's also one of the options in the CMAC and Wolf scheme. And you can see most of these schemes are doing a pretty good job. The results are lying in the diagonal lines here is 1-to-1. But if you zoom it up, you can see some differences. And here are the difference tables. The SNAP scheme for different kind of microphysics give you about 1 to about 7% errors, which is much smaller than the scheme in the CMAC. And also it can actually be more accurate than the numerical method, the Gaussian quadrature scheme. Okay. And the time needed for SNAP is about the same as the BS95, 10% more than theirs. Okay, but about maybe that's about only 5% of the Gaussian quadrature scheme. And from our scheme is trimodal, three-moment, not trimodal, sorry, three-moment and multimodal schemes. From the moments, we can retrieve the size distribution. So this is the initial size distribution, and we let it evolve by Brownian coagulation. Okay, and different schemes seems to do pretty good job, but you can still see some differences. And the dark line here is calculated with spin model, which is supposed to be the most accurate. So we use that as a truth. And you can see that our scheme produce result very close to the bin scheme, only less than 2% error. Okay, and it's slightly better than the scheme in the CMAC. Okay. Next, I'll show you some example of the aerosol-cloud interaction. I already showed you one that the aerosol influence on the typhoon Neri, and here I'll show you influence from ice nuclei, and also the model here, the aerosol will be generated by the model, so it's a fully coupled scheme. Okay. The same scheme here. We use that model to study the effect of two types of ice nuclei. One is the mineral dust. So our model included dust deflation scheme in the original model, and here is the dust storm case, and following by a frontal system. And we'll try to see how those dust affects the precipitation from the frontal system. And the nucleation scheme for dust to produce ice follows a traditional theoretical formula. But in that formula, we use two factors from observation. One is the activation energy, and the other is contact angle contained in the F factor here. You don't need to know the detail, but to know the nucleation scheme, we only need to know two thermodynamic factors, that is the activation energy and contact angle. And for those two parameters, we searched a lot of the experimental data and do the fitting. And these are the results that we got and compare with the observation. The dots are from the laboratory measurements, and the thin line here are from our formulas. You can see it fits pretty well. So we put that into our model and see how that affects the cloud microphysics. And I will only show you the results with pure mineral dust, minus that without the dust. Okay, you can see with the mineral dust create a lot of cloud ice and lots of snow and graupel. And because of the increase of ice, it depletes the cloud drops. So you see less cloud drops. and less rain at the top. However, in the lower part, you see much more rain because of the melting from snow and gravel. So the end result is to enhance the precipitation over the Taiwan region. Okay. And this is for pure dust, but we think the dust, when transported from the northwestern China, come to Taiwan, it must go through the polluted area. So the dust must have internal mixing with the pollutants. So next simulation, we show the mixed dust effects, subtract the no dust effect. See much more cloud ice, snow, and gravel. The effects is more significant than the pure dust. Okay. And of course, then more precipitation on the ground. And these are the net results for effects on precipitation, the short wave, and the long wave. Okay. You can see the results are very significant. The bottom panels are the dust effect minus those without dust. As you can see, the significant increase in the precipitation, decrease in the short wave, and increase in long wave. Okay. Okay. And then the next example is the phytoplankton. That's the very small creatures in the ocean, the plankton in the ocean. And some of the experiments show that those plankton are very good ice nuclei, okay? And their efficiency can be better than the mineral dust. However, their quantity might not be so much, especially over the land, because over the land there are a lot of mineral dust. But over the ocean, we think the main source of ice nuclei could be from the phytoplankton. So this is a simulation try to see how much phytoplankton can be generated in the atmosphere and how that affects the clouds. So we use the sea spray skin to generate sea spray. Then we use the chlorophyll concentration observed from satellite to infer how much the phytoplankton is contained in the sea salt, and use that to generate the ice particle. So this you can see the generated phytoplankton near the surface is around the maximum wind of the typhoon. For this case, this is a typhoon CPAT. And these are the phytoplankton three-dimensional structure. This one we did not involve in creation. Okay, and for those two we included the ice nucleation scheme. And these are the phytoplankton in the cloud drops, and this is phytoplankton, interstitial phytoplankton. One of the main features you can see the difference between these two, that if we include the phytoplankton, actually the phytoplankton goes much higher. Okay, and I'll show you why in the next diagram. These are the vertical structure of the hydrometeors. Let's focus on the blue, light blue, and the dark blue. That's the cloud ice and snow. Okay, without the phytoplankton, you don't see much ice at the top here, but even cloud drops are much less. But if you include the phytoplankton, you see a lot of ice at the top. And we think one of the reasons is that when the ice nuclei generate the cloud ice, make the cloud glaciate, and then it causes more latent heat release, so the cloud develops much stronger. Okay, but here if there's no ice, the cloud is much shallower. So we think at least in this case, the phytoplankton can actually influence the structure and the intensity of typhoon. And there will be one poster discussing the details of the effects. You'll see the change of precipitation is actually 200 times more. However, this is only a preliminary study. We did not include the rain-out effects of the phytoplankton, so the actual effect should be smaller, but it still can be quite significant. So in summary, we developed a cloud microphysical scheme and the aerosol microphysical scheme and coupled them into the WRF and WRF-CAN model. And the skin now we are still on the process of improving it, including the effect of the ice crystal shape, and also we try to make it a 3-moment skin so that the simulation of a hail can be improved. And we also do a lot of applications of the model showing that the anthropogenic condensation nuclei can affect typhoon, okay, mostly through the effect of latent heating, and then which influence the track of typhoon. And we also show 2 types of the ice nuclei, the phytoplankton and mineral dust, both can have significant effects on the cloud microphysics and radiation. Thank you. Questions? 2? That's missed 1. Okay.
Now, I'm curious, for typhoon Mary, did the intensity also decrease by aerosol?
I'm not sure. The intensity is not significantly changed.
But it's broader.
It's, at least from the simulation, yes.
What's the causes for the broader?
Because the aerosol enter the outer rain band first, and it enhances the outer rain band development, especially the envelope part. It creates more latent heating, so generate more vorticity. So the outer rain band develops faster and depleted the water vapor, so it cannot get into the eye. That's what we think. Other questions? Paul?
Actually, I have 2 questions. One is, how is your trimodal scheme different from the Milburn and Yao's? They also have the trimodal, right?
Okay.
Okay. Should I?
Let me
go
first answer the first one.
first
Actually,
one?
our cloud microphysics scheme is so far is 2 moments, not 3. But we are in the process of changing to the gamma distribution, which is a much better distribution.
Okay. The second question is, it seems that your model produced very good result in the regional scale results. What I'm worrying about is how would this do when you incorporate it into the climate model things? Like people work on the satellite data before, and often that sometimes too detailed data sometimes does not improve the forecast, and I suspect sometimes this may also happen. You have very good model in terms of regional scale, and that may make the climate prediction worse than you would like.
Right.
Could that happen?
Yes, of course. Because we are trying to develop the schemes from the basic physics, okay, we do not try to do any tuning. So when we include the better physics, it probably will destroy the original tuning. So it could give you a worse results. But our purpose is not to make forecasts. We try to improve the scheme. So in this way, we can find out more problem with the models. So get rid of the original tuning one by one. That's what we hope. Minda?
You studied the impact of mineral dust and phytoplankton. How about sea salts? Are they important?
We did some experiment on sea salt itself, but it doesn't show much effects, at least in the previous case we indicated. The sea salt only changed the warm clouds, but the typhoon already have very strong warm rain process. So the sea salt actually doesn't change much of the microphysics. But it does if the ice phase are involved. No more question? Okay, then let's conclude the session this morning, and let's wait for the lunch, shall we? Thank you. Any announcement?
没有变成